Welcome back, guys, to part 3 of Goals and Necessities. My name is Luis Ricardo. I'm the producer at Wirezapp. In the last tutorial, we ended with implementing positive goals. In this tutorial, I plan to implement negative goals, do some slight architecture changes, and hopefully start on world implementation. After the last tutorial, I've noticed that there were some issues with my implementation. I could have done it a lot easier just using an array. So we're going to want to define a new class. We're going to call it attribute. And we're going to say attribute has, and we're going to say it has a few properties. We're going to say it has a property called name. It has an int called value, and it has an int called delta. Okay. This is just small architecture change from the last one, just so that we can make things easier later on. So now I'm going to delete this. Value. Because time aspect is a little harder to compute using this method. Using this slightly different architecture change, which is why I didn't want to go into this right away. Need to put another for loop in here. And I'm sitting, and the only reason why we're doing this change is because it allows us to eventually make this infinite access. Attributes size. What am I doing? J is less than J plus plus. So now what this time aspect does is it takes an array of the time aspect, assuming each axis of your array. So it goes through the entire array, calculates the time aspect, and then you cancel out the time aspects that you don't care about for that axis. So down here you can see that for dollars, we're weighting it based on health, and obviously we're not going to take the average including dollars again, so we're just going to cancel that out. You can pre-compute time aspect if you wanted. It's in this scenario, it's such a small difference, it doesn't even matter. So another issue with this is the score function. We go back over here, time aspect is already automatically included in. So the way to work around that is if you have a static for pre-time aspect score, you can say input input 1, input 2, and for pre. Now all that we're going to do is it'll be exactly like score over here, except we won't be returning the time aspect. So it's everything of score, the entire function, not this one though, because we're just multiplying it by the time aspect here, which is what I was saying before. You can multiply it by the time aspect later, and it won't make a functionality difference. It'll look different. We can do equals time at, no, These functions time aspect add completion time. This attributes 0 delta. The completion time is still weighted based off of how quickly your food goes down. You can change that anytime you want. No, that should be value. Yeah, so that should be value. And then we can just say attributes j dot value attributes j dot delta. So does the exact same thing that time aspect did down here. You can see, yeah, I still have hello worlds because never changed that. So it takes a delta and the entity value, and then the temp is, in this case, just the input score. Well, no, the temp in this case is your delta value. That's just making sense. The temp in this case is the actual value that you're putting in. So it's like it's the thing that the advertisement is saying, hey, here's how long I'm going to take. It's just reorganizing it. Nothing else it does any differently. Okay. Now, we can just copy this. And this does what I was saying before, which means as long as add dot positive costs dot at I dot type, which means it'll weigh all of your time completion aspects besides the one that you're putting in. So if you'll die of socialization before before it's completed, then it would rank that. Yeah. So just make that size. Yeah, sorry I had to do this again. This is ridiculous. Okay. So now we're just going to pass this value, m. Well, first we have to do m divided equal by r dot size minus 1. Okay. So this is our average completion, average completed weighted score. So then we can just say, hey, we are going to monetize this using the slightly modified version of the score function. So pre-time aspect score, score 1, score 2, so current score, future score, m. Okay, so we can get rid of this. It's a pretty big shift. Alright, so as for negative aspects now that we've taken care of our architecture change, we don't really have to worry about this anymore. It's sort of self-handling now. But, what next? What next? Okay. So we're going to do negative aspects. Float k equals 0. We're going to say k is our average negative score for this advertisement. And then we're just going to do a generic for int I equals 0, I is less than add dot negative cost dot size I plus plus. And then just to save some advertisement, we do auto just to save some space, we do auto add equals add dot net cost equals add dots. Ah, damn it. It's keyboard. Negative cost at I plus plus. No, what am I doing? Okay. Okay, so now we're going to say that if negative cost dot return value plus attributes times attributes at I delta, this one's value, are greater than, oh wait, no, that should be something different. That should be this. So completion done. So if our return value is if our return value plus the amount of attribute we'll be using during this time to complete the task is greater than what we currently have, so attributes dot at negative neg cost dot type dot value. So if it kills us before we can complete it, or we could actually just say greater than or equal to, a little easier. We're going to return 0, which means it's done. It kills us. We don't want that. That's bad. And then if it doesn't, here's where the scoring part comes in. Scoring part. So how negative scores are usually calculated with something called the sigmoid. It's basically an S function. It looks like an S. Some of them are a little complex, some of them not so much. But what I do differently is, as the difference gets higher, as it costs you more money or whatever, it gets weighted more strongly. So for the highest weight, I use error functions, which are the brown line going up there. As you can see, it has the farthest distance from like the I would say regression line almost. Not this regression line, a regression line that would go right through these. But yeah, and then for the lowest one, I use this function over here because yeah, okay, it takes away 5 hunger. Well, we have 90. It's not that much. So I refer to this as auto-weighted score. Just it's intuitive. Let me get my other project out. So I'm just going to show you the code first. There's really nothing in here that we won't be going over at this point. Alright, so for auto-weighted score, the L is our current score. So that's what we're trying to weight off of. Now, if it's less than 20, you're only going to use error functions, which is the strongest weighting. If it's less than 30, then you use mostly error function, but you'll be using a little bit of 10H as well, just because it's sort of like a gradient area. It's a gray area between the two. If it's less than 50, and then obviously greater than 30, you're going to be using 10H. If it is less than 60, but greater than 50, it once again scales depending on its distance from that critical point, and it calculates the error function plus the absolute value function and returns that. If it's anything greater than 60, it just returns the absolute value function because it doesn't really think it's very important. Clean and simple. Just helps the AI stay alive. So now we're going to implement that. Actually, I think we just copied it over, probably. Yeah, re-implement it. Oh, no, first I have to implement the other one. I'll do one first. Static auto weight negative. Where is it? In current score. Input score. And now what input score is give me 1 second. What input score is t. T is, which is why I was saying the negative are dependent on the positive. T is this right here, and that's what we're going to be putting in as our input score because, well, yeah, if you're outweighed by the negative values, then it'll no. If the positive values are so good that the negative values shouldn't really be considered that heavily, well, yeah, go for it. Okay. Input score, int cost, and int entity value. Oh, let's make that a float. Okay. Now we're going to say if current score is less than or equal to 20. Oh, we will only use error functions. So we're going to return error function input score cost entity value. Okay. The error function is very, very simple. It's just a straight up implementation. So I'm going to do static float error function float input cost, no, do int cost int entity value. Okay. So now if the cost is greater than the entity value, we are going to return -1 because this will kill us in one way or another. It'll kill us, it'll upset us, it'll do what it wants. I'm going to say float var equals now because our input value is going to be a decimal 0 to 1, and if you can see, let's explore Chrome. If you can see over here from 0 to 1, so this is 0, 1, you don't get the full range of data. So now we need to scale it so that it goes all the way back from -2 to +2, just so that we can say, okay, if it's the maximum value, return 1. If it's the negative value, return 1. Instead of saying, okay, if it's the maximum value, return whatever that's 0.7, 0.8, and if it's the lowest value, return 0. We don't want that. That's stupid. It should be lowest value, give it a negative score, and then all of that. Oh no, not a negative score. If it's the lowest value, we still want 0, just because we don't want it to factor in. We want to say, okay, this is 0. This will do some serious damage, but it won't do as much damage. It's a negative score. So it'll still return 0, but at least it'll still go up to 1. I don't know, that's not making much sense. Okay, so now let's just do some basic translations. Float cost divided by float entity value times 4 minus 2. Okay. Ooh, they meant to parentheses? Okay, I did. Yeah, I did. There we go. Okay. So now we're going to actually apply the error functions. We're going to do float var equals float. By the way, in case you're wondering, the reason why I'm typing this upper line is it's just easier to debug if something goes wrong. And I would be surprised if I don't mistype something somewhere. Okay. So, I don't particularly know the reason for the pi divided by 2. It meets the sigmoid requirements better with the pi divided by 2. Well, square root of pi divided by 2, so let me fix that. Okay. And now we're going to say var plus equals 1. That way, in case it did return -1, it'll move over to 0. Over to 0. But it'll still be within this general range. So now we're going to do 1 minus that, so that it flips the graph. So it goes like it's a backwards S instead of a straightforward S. Because we want to say the lower the difference, the higher the score is going to be. So the less it kills us, the higher we're going to be. So we're going to do return 1 minus bar times input. Here we go. All right. So now we're going to do the translation for less than 30. Okay. Current score. We're going to say 10H, and we're going to say, okay, I just want to make sure. Error function. Now the reason this is here, as I said before, error function is done in gradient, which means the further away you move from 20, the less dominant ever force it becomes, so less scaling is needed. Alright, now we're going to make a 10H function, and it is going to be the exact same thing. So I'm just going to copy this, because once again, same scaling needed, fits in the same confines, don't need to explain it all again. So I'm going to do 10H, and I'm going to do 10H. Okay. Okay, there we go. Okay, so now for the next part of the gradient, we are going to have else if current score is less than or equal to 50. Now obviously you can play around with these numbers. You can even have another structure that takes these numbers for you so that it scales differently. Let's say that you really you want the AI to very much keep the food above 70. well, then you just change the scaling. So you change the numbers to like 70, 80, and 90. That way the AI is like, oh yeah, this takes priority. I should do this first. Okay. So now this is just going to be this. And obviously t is a gradient value up there. I don't need to define that. Okay. Now if it's less than 60, I'm just copy this in. Ooh, I appear to have made a typo. So that should be that. Typos like that. That's why you do error checks. It was working fine with error function. It was living. Okay. Now this is going to be the only function that's actually different. Well, I mean, you still have the scaling. All that is still done. So I'm going to copy that part. I'm going to say this is x plus abs x. Okay. And I'm going to say var equals var divided by 1 plus abs var. Obviously, you can compress that. I can do. I'm just leave it there. I'm always. Oh, it's a little sloppier. Yes. Is it easier to debug? Yes. Leave it. But to be honest, I don't really need to debug it at this point. I have to go and do not disturb. Okay. So now we have our auto-weighted function, and we can just say then if it's anything else, no need to calculate anything in gradient, just return on x plus abstract x. Eventually, I'm going to make this automated more so that I can just keep on throwing in new functions and telling it this is where the gradient starts, this is where the gradient ends. But for the time being, that's what we got. Okay. Now we can finish up on negative functions, and then we're going to maybe move over to a little bit of world implementation. Okay, so we're going to say k plus equals monetization. No, what am I doing? Needs functions. Auto-weighted negative, auto-weight negative, current scores maybe. We're going to say this is average. Our input score is going to be T. Our cost is going to be a very nasty function that I already defined. Yeah, very nasty combination. Which is defined there. And then we are going to say that our there we go. Huh? Is it miscounting? Huh, I think it is miscounting. Okay, that's a little weird. Oh no, there. Okay, and then our entity value is just going to be plain and simple neg cost dot type attributes dot at in case you haven't noticed already, negative scores are a little bit more strongly weighted than positive scores. It's just a little closer to real life, in my opinion. No other reason. Yeah, it's a damn good reason, but oh, forgot one little part. That's did I? No, this. Okay. So this is the same thing over here. That this will be our future value after everything is said and done. Well, this is how much it's going to go down by after everything is said and done. That's what's put into K. And then we have K is divided by the size of the negative cost that we have. Same thing that we did with T. And we're going to return T times K. Okay, there we go. We have our entire negative function. I think this is actually a good place to stop. In the next video, we will implement our entire container structure, which is our world, structure. And the video after that, we'll start working on an architecture for multiple entities. It's a pretty big shift from what we have here right now. It's a lot more complex, so I didn't want to go into that right away. Okay. Thank you for watching. My name is Luis Castricado. I hope you enjoy your day. If you want to join the team, send me an email at projectfaramid@gmail.com. Follow me on Twitter at twitter.com/WireZappGames, 2 Ps. If you want to follow me on Facebook, my Facebook is facebook.com/projectfero. And finally, if you want to follow me on Tumblr, my Tumblr is wirezappgames.tumblr.com. Thank you for watching, and goodbye.